All right, hello class. Let's start um, doing the second video here. We're going to continue on momentum, and we are going to solve a collision that requires to treat the motion in two dimensions. And to do that, I'm going to borrow the idea from billiards. And if anyone played pool before, usually you have one ball that you are allowed to strike to hit other balls. So let's say you strike this red ball right here into a different ball that is not moving. And depending on the, and so this is, we're gonna call this an initial. So this is an initial. Uh, Initial condition in which the ball is traveling to the right and it's going to hit this one, and depending on the angle it hits, it's going to scatter. And what I mean by scatter is that they will move in different directions. Let's go ahead and draw some possibility of the final. So now you have the two balls here, and we find that now this is final velocity, and we have some final velocity. Now, to make the discussion easier, I'm going to call this one the red ball, ball number one. I'm going to call the blue ball, ball number two. And I'm going to call this situation right here the final state. All right. So when I say let's continue momentum and solve a collision in two dimensions, what I mean by dimension is this. If you imagine this first case and just draw a line connecting the dot. Our previous video, the two balls were confined to move in this straight line. They could not move up and down. But now we're talking about billiard balls on the table. Now if you draw the same line here, you can see that if this has velocity this way and this has velocity this way, they're moving apart, right? And if they're moving up and down, that means that they're also allowed to move up and down. And that's what we mean by two dimensions. We mean an x dimension right here and a y dimension right there. So y is also included here. And you are familiar with this concept already. If you remember what we did for ballistic motion, for example, in which you had to treat the velocity vectors as two-dimensional objects, you went ahead and did, x direction, y direction, and you broke the components. So that's more or less what needs to happen here as well. Okay. So to do this as a problem, let me define a few angles here. So I'm going to call this first angle here theta. I'm going to call this other here angle phi. And I have to tell you now that theta is 30 degrees and that phi is 60 degrees. And that is completely dependent on the moment in which they collide, somewhere in between here. And it all depends on the angle of approach and all of these things, but we're not, remember, if we're going to solve this as a momentum problem, the information about the collision is one, not important, and two, most of the times not attainable. Good. And another thing I'm going to point out is these are billiard balls. So if you all when you're playing pool, all the balls are the same. So mass 1 and mass 2 are the same. So I'm going to just add that as an additional piece of information that you need. Mass 1 equals to mass 2. So this is a problem I would expect you to be able to solve in your homework, in which I have, I give you some initial velocity here. I'm going to give it to you right now. Let's say that this is 2 meters per second. And this is a velocity, so it's in the x direction. And it's this velocity right there. Now, initially, this ball is not moving. After the collision, you have a velocity final of object 1, and it is, we know that it scattered off from the collision at 30 degrees. Now we have ball 2 has a velocity 2 final that is 60 degrees below the x direction, and that's why I wrote right there. With this information and conservation of momentum, you ought to be able to tell me what the velocity of object 1 final is and what the velocity of object 2 final is. And that's what we're going to do. So before we do anything with this, I want to show you how I like to think about it. So I like to set up a Cartesian coordinate system, initial and final. You don't have to do this. It's just a way I found to keep myself organized. So let's do this. So for I'm going to set a coordinate system here in x and y. Good. That should be good enough. And now I'm going to say, okay, well, this is x and y, and this is initial. This is x and y, and it's final. If you remember, we did do a lot of free body diagrams in this class, and a free body diagram is basically using the fact that forces are represented by vectors. Every time you have anything represented by vectors, you can take the vector itself and move it to the center of the coordinate system just so that you can make sense of it all. In this case, we're going to do the same thing because velocities are vectors. So we're going to go ahead and take every vector, initial, every vector final as far as velocity, and point it in the center of the axis. So this is velocity 1 initial. Velocity 1 initial is completely over here in the x direction. Initial. Now, ball 2 is not moving. So initial, you only have one vector. So let's draw the final one. The final one is this one right there. Velocity final 1. And you have an angle theta there. And so let me go ahead and draw velocity 2 final. Now these angles are not very representative. I'm not being very careful about how I'm drawing this. This is just a concept thing. Velocity final 2, right? Good. So these are going to come in handy very, very soon. So now that we have masses, mass 1 equals mass 2, we have the two angles, and we will know what we know what we're looking for. We have these two velocity diagrams. We can abandon the original statement of the problem and work with what we have. And just as a review, remember that momentum is the amount of motion equals to mass times the velocity. And every collision, momentum will be conserved. And if you remember the statement for conservation of momentum, it is that the sum of all the initial momentums needs to be equal to the sum, total sum of all final momentum. Okay? So we can go ahead and start decomposing this then, right? So we have two objects. So let's go ahead and do that. We have two objects. So the total momentum initial is the contribution due to both objects, which means momentum 1 initial plus momentum 2 initial, right? And in the final situation, we still have two objects, which means that the total final is a contribution due to two objects. Momentum 1 final plus momentum 2 final. Great. Now, every time you see this momentum, it's a mass and a velocity. So we can go ahead and open this up even further. So momentum 1 initial is mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, equals to mass 1, velocity 1 final, plus mass 2, velocity 2 final. All right, and this is the point where you have a bunch of numbers from your problem, right? You have angles, you have velocity, speeds in this case, and you want to be able to put that in a certain equation to be able to solve this problem. And at this point you realize, well, I'm stuck with vectors, and I want to get rid of those vectors. And this is the point in which this diagram comes in useful. Because in our first video, we could go ahead and turn these vectors into plus or minuses because we were confined to move left and right into a single dimension. However, we have an additional degree of freedom, which means that we can move left and right or up or down, which means that for each dimension we have one set of equations, meaning that velocities for this problem are have both components in the x direction and the y direction. I did not specify the x's, but it is implied that this is x and this is y. Okay? This is where this diagram comes in useful now. It allows you to see what has x components, what has y components. Okay, I took the time to recreate the drawing we had up here, down here, just so that you can follow closely how we're going to decide what each term is going to be. So let's do the x direction first. Remember what I said, these equations now are vector equations, and to take them into scalar equations, you have to do each direction independently. And we have done this in forces and in ballistic motion, so you should be used to this by now. So in x, let's go ahead and see the velocity initial here. Do you see it's completely, everything is in the plus x. So this whole term here ends up showing up here. V1, velocity 1 initial. Good. Now, velocity 2 initial, that is the velocity of object 2 before it gets hit. It's 0. So this whole term goes away. So in this case, this is 0. We can go ahead and say equals to mass 1, velocity 1 final. Now I want to show to you the velocity 1 final is the x component here of this vector right there. So it's this one. And if you imagine a triangle here that has to do with the velocity 1 final multiplied by a cosine. So this whole term here ends up to be mass 1 cosine of theta velocity 1 final. Good. So then we can go ahead and do the same thing for velocity 2 final. Velocity 2 final the x component is this one. Oh, is this one right here. This is a shorter arrow here because it is steeper. And if you imagine a triangle right here, this is proportional to the cosine of phi. So I'm going to say mass2 cosine of phi velocity to final. Great. So let's go ahead and do the y direction. So in y, velocity 1 final, velocity 1 initial. Velocity 1 initial is completely in the x. So this term is 0 as far as motion going up and down, right? Velocity 2 initial is 0 inherently. The object is not moving whatsoever. No direction, no directional movement whatsoever. So this whole side of the equation here in the x direction is 0. Excuse me. There we go. It's 0 equal to, and now we're going to look at the y directions, the y components in the final velocity. So now the final velocity, if you look at this one, the y component for this one is right there, points up. So it points up, which means it's positive. And if you imagine a triangle like this, right here, this is proportional to sine. So this will be mass 1 sine theta. Good. Now, if you look at, so we just did this. So mass 1 times velocity 1 final in the y direction is m1 sine of angle velocity 1 final. Okay, good. The final term here, mass 2 times velocity 2 final. This one right here is this vector right there pointing down. And if you imagine these making a triangle, this is proportional to the sine of phi, but it points down. So I'm going to say that this is minus mass 2 sine of phi velocity 2 phi. And there you go. Now we have basically pulled everything from the problem. So we pulled everything from it, and now we're left with this x and y. Now I'm going to remind you that the things that we do have and don't have here. So let's take this one. Okay. First of all, we have, do we have mass 1s and mass 2s? We don't, right? We don't have mass 1 and mass 2. But what we've said before is that these are billiard balls. And billiard balls, mass 1 and mass 2 are the same, right? So let me just remind you that mass 1 equals to mass 2, which means that if I take this whole equation here and divide by mass 1 goes away, mass 1 goes away. This will be mass 2 over mass 1, but mass 2 equals mass 1. This goes away as well. And the same thing, and you can convince yourself that the same thing will happen here, right? Good. Now we have a problem because this is V1 initial we have is at 2 meters per second, right? Cosine of theta is 30 degrees. We have this one. Velocity velocity 1 final, we do not have this one. This is something we're trying to find. Cosine of phi, we have that one. This one we don't have. That's something we're trying to find. So right here, you know you have two variables in one equation. You cannot solve this equation. So let's go to the next equation. Sine of theta. Theta is 30 degrees, so we have that. We don't have this one. That's something we're trying to find. This one is sine of 60. We have that one, and this one we don't, right? Again, you have two variables, one variable here, one variable there, and you cannot solve. But here's what we do have. We have two variables and two equations. And as we said in class, every time you have an X amount of variables, you need an X amount of equations to be able to fully determine what they are. Here we have two variables, velocity 1, the speed 1 final in this case, and the speed 2 final. These two variables and two equation systems is fully defined by these two x-y equations. And this will happen almost every single time when you solve collisions in 2 dimensions. You will need to include both dimensions and solve for them and use one equation into the other. All right, so there's no, now it's down to your preference and how you solve this. You could solve for V1 final, put it into this equation, solve for V2 final. Or you could solve for V2 final and do the same for V1 final. So I'm just going to go ahead, pick a color, and pick one way and just carry out the calculation for you as an example. If you'd like to pause this video at this time and practice in trying to find these two variables by yourself, that'd be good. Then if you can't figure out, follow what I do and then do the opposite. And what I mean by that is this. So let's go ahead and pick V2 final. Let me solve for V2 final. If I move this whole thing to the left side of the equation, I get sine of phi V2 final equals to sine theta V1 final. What I'm going to do here is I'm going to solve for V2 final. So one more step, you can show that V2 final is the sine of theta divided by the sine of phi multiplied by V2. Let me be careful here. V2 final, divide that V1 final. Now, I'm going to take V2 final right here and substitute, and it came from this. Remember, it came from this equation. This equation here turned into this, and now I'm going to take this right here, and I'm going to substitute for this right there. You see that? Now, if you want some practice after you see this video, the one thing you could do is you could solve for V1 final, and then you could plug it in here and see if you get the same answer, because you should. It does not matter which variable you solve for first. You should always get the same answer. So let me go ahead and I'm going to take the same color here as green just to drive home the point that we're taking precisely this equation right here. So V1 initial equals to cosine theta V1 final plus cosine of phi. Now this V2 final here is this whole expression there. Do you see that? So I'm just going to go ahead and write that. So this is sine theta, and now this whole thing is divided by sine of phi multiplied by V1 final. Okay, so we are almost done. We now need to solve for V1 final. Okay, this is a good point too if you want to get from this to the next line that I'm going to write, because I'm going to skip a few steps, but I'll describe what the steps are. the sine over cosine, that's going to be it's going to turn into a tangent in the denominator. Then you're going to have cosine theta, sine theta divided by tangent. And then do you see how this is, you can undo a distribution right here and pull V1 final out? That's what I'm going to do. So I'm going to rewrite this out. V1 initial equals to, now there's a whole bracket, cosine theta plus cosine phi divided by tangent. Nope, made a mistake. This is cosine theta. Nope. All right. This is actually sine theta because if I'm going to combine a sine and a cosine, they have to be the same angle. So this is divided by tangent phi. Multiply by V1 final. Do you see? And to go, if you're having problems seeing how I went from this line to this line, all you can do is you can take this variable, you can distribute, and then open this tangent into sine over cosine, and you get this line again. So this now, this whole thing under the parenthesis here, this is just a number, right? So this is just a number, so I can just take everything in the parentheses and divide both sides of the equation by that. And when I do that, I get completely the format of one of our first answer. So velocity 1 final equal to velocity 1 initial divided by cosine theta plus sine theta divided by tangent phi. Okay. All right, and so now all that's left is to evaluate this for the numbers we have. And if you look at the numbers we have, this comes down to 2 meters per second divided by the cosine of 30 degrees plus sine of 30 degrees divided by tangent of 60 degrees. And this is approximate 1.73 meters per second. Now we found V1 final, and remember, you're not done yet because we need to figure out what V2 final is. And to figure that out, we need to take either of the one equations and solve for it. We kind of already have it. Where is it? Do you see this one right here? I'm going to borrow that. Do you see this one right there? We just found V1 final. We have this angle, we have this angle. So V2 final is just that. V2 final is the sine of theta divided by sine of phi. I can probably just go ahead and do that. So for our second answer, V2 final is the sine of theta divided by the sine of phi multiplied by V1 final, which is precisely what we just found. So then if you go ahead and you evaluate this, then sine of 30 degrees divided by sine of 60 degrees multiplied by what the answer we just have, 1.73 meters per second, and you get basically 1. So it's 0.998, but there's no point in really saying, like, it's basically 1.0 meters per second. It is close enough, right? Okay, so now we have these numbers, right? And I wanted to think about what these numbers mean. This V initial final and this V2 final is the length of the arrows. So if we have the Cartesian for the final case, and we do V1 final, the length of this arrow is 1.73. And remember, this is an angle of 30 degrees. Now, if we think about what we just solved here for V2 final, this angle is 60 degrees. In V2 final, the length of this arrow right here is 1.0. So let's say you're doing a homework or an exam or something. And you can see we went through a considerable amount of algebra. And you want to make sure you got the correct answer. There is one very good fail-safe way of doing this. And that's just by thinking about what it is that you're doing as far as momentum conservation. So this is the original drawing, right? So this is the velocity. So let's go back to the original drawing. There you go. So this is the original drawing. Initially, you have all of the momentum in object 1. Object 2 has no momentum. Now, momentum, if you remember, is an amount of motion. That motion has a magnitude and a direction. And that direction is only in the x, meaning the amount of motion total of both of those objects is only in the x direction. Let me repeat that. Because the object number 1 is the only object that has momentum, and it only points in one dimension, and object number 2 has no momentum, meaning that their combined initial momentum is only in the x. And the final momentum has to be the same as the initial. Means that when object 1 and object 2 start moving in the y direction, the momentum of object 1 and the y and the object have to be exactly the same amount in opposite directions as object 2. Meaning that if you take the final momentum in the y direction of 1 and you add to the final momentum of y momentum of 2, you need to get 0. You do. Because initially you have no y momentum. Okay. So then you went ahead and you really understand the concept of momentum, but now you're looking at these numbers and you're trying to figure out if these numbers are correct. That means that this arrow right here, which is mass 1 multiplied by, it's just the y component of the initial momentum. This is m1 sine of 30 degrees multiplied by V1 final. V1 final is our 1.7 meters per second. It needs to be equal. It needs to this other part. What is a good color? No, let's try something else. Hold on. Okay, it needs to be this component. It needs to be mass 2 sine of 60 degrees multiplied by 1.0 meters per second. Okay? And again, mass 1 and mass 2 is the same. Right? And you can try this out. You can try this on your own. So if my answer here for A or B is incorrect, this will never work out. Okay? So this is just basically saying, look, the total momentum final, if you add both y components, have to be 0, which means the y components in the up and the down direction have to be the same. All right. Good. So I hope that you can. I hope that the steps here are not completely new to you. We borrow a lot from forces in which we have to break x and y components, and the only difference here is that you're not breaking x and y forces, you're breaking x and y velocities. All right. So you should go ahead and try to work on this example on your own and see if you can help. I should come up with another video with an example of a different problem in 2 dimensions, just because this is one of the more algebraically intensive things we're going to do. All right. Okay, very good. I will talk to you all soon. Have a good day.